Hello, this is Mrs. Nearing. We're going to do a short video on combustion analysis, which is another method of determining the empirical formula of a substance. So what happens in combustion analysis is you start with a hydrocarbon, which is something that's made mainly of carbon and hydrogen, and you combust it in the presence of oxygen. And when you have a combustion of a hydrocarbon, you'll always form CO2 and H2O. And something that you should notice is that the carbon over here on the right, you only have carbon in one molecule and you have hydrogen just in one molecule. So what that means is that all of the carbon from our original hydrocarbon ended up in this CO2 over there, and all the hydrogen from my original hydrocarbon ended up in the water. So if you can measure how much CO2 and H2O are made during the combustion reaction, you can figure out how much carbon and hydrogen were in your original sample, and that will allow you to determine the empirical formula of the substance. So here are some general steps to doing this. So you're going to have some data about how much CO2 and how much H2O is made. You can use your CO2 mass to figure out how many grams of carbon were made using the mass percent of carbon. You can do the same thing for hydrogen in your water sample. So if you've got 2 grams of water and you find that water is 10% hydrogen, you can figure out how many grams of hydrogen were in your sample. And if applicable, you might have a third element in your hydrocarbon. It might be oxygen. It could be something else like bromine or chlorine. And you can figure out the mass of that third element by simply subtracting. So you're going to have the mass of your overall sample. And this will make more sense once we go through an example problem, but you can come back to this page later at your leisure to kind of get a sense of what steps you might take. So here's a practice problem which we're going to walk through. So let's kind of break down what we know. So we've got caproic acid. It's made of carbon, hydrogen, and oxygen. And we don't know what the mole ratio is, what these subscripts should be. But we do know that we have a 0.225 gram sample of this acid. So my total sample of acid weighs 0.225 grams. And that when I combust it, I get 0.512 grams of CO2 and 0.209 grams of H2O. And we're trying to figure out what is the empirical formula. So we're trying to answer the question, what are those subscripts there? Alright, so my first step is I'm going to figure out how many grams of carbon I had in my original sample. I know my grams of CO2. I know that that's 0.512 grams CO2. And there's several different methods you could use at this point. But one method I think might be the easiest is you could use the mass percent. So you could say, well, I've got 0.512 grams of carbon, and of carbon dioxide, and say what percent of that carbon dioxide is pure carbon. And the way that I would find a mass percent is I take the mass of the whole sample, which is 44 grams, divided by the mass of the part, which is 12 grams. So this would be how we'd find the mass percent of carbon in CO2. And if you pause and plug that into your calculator, which I'm going to do with you here real time, divided by 44, this is 27.3%. So what we're saying is that carbon dioxide sample is 27.3% carbon. So if I take 27% of 0.512, what that means is I have 0.1396 grams of carbon. I should round that to, 0.140 grams of carbon. Okay, so that's how much carbon I had in my original sample over here. Let's look at our hydrogen. So I've got 0.209 grams of water. And what percentage of that water is hydrogen? Well, water weighs 18 grams. The hydrogen piece of that is going to weigh 2 grams. So if you plug that in your calculator and get a percentage, what we're saying here is that water is 11% hydrogen by mass. So what's 11% of 0.209? You get 0.023 grams of hydrogen. So put 3 sig figs there. So what we know is we have 0.14 grams of carbon, we have 0.0232 grams of hydrogen, in our original sample of caproic acid. Because remember, all of the carbon over here came from the sample over here. So if I had 0.14 grams on this side, I had 0.14 grams over here. You might notice that these two numbers don't add up to 0.225. That's because there's this third substance right here. So to find the mass of the third element, you would take the total mass, 0.225, and subtract the mass of the carbon, which is 0.410, and then the mass of the hydrogen, 0.0232. So this is the mass of the carbon, this is the mass of the hydrogen, this is your total. What is left is going to be the mass of your oxygen. So we've plugged that into your calculator. 0.225. I get that I have 0.062 grams of oxygen. Alright, so to summarize what we know at this point, we have 0.140 grams of carbon, we have 0.0232 grams of hydrogen, and we found that we have 0.062 grams of oxygen. If we add those all up, we should get 0.225 grams. That was our total sample. And now we want to convert these numbers into a mole ratio. So if you think of what our steps are, percent to mass, mass to mole, divide by small, multiply till whole. I already have a mass, so we get to skip the first step, and we just go straight to the mass to mole step. So to convert mass to moles, I'm going to take 0.40 grams divided by the molar mass over here. And if I divide these values by the molar mass, I will end up with the number of moles of each of my... Alright, so at this point I have 0.0117 moles carbon, 0.023 hydrogen, 0.0038 oxygen. So to convert these values into a nice, neat whole number ratio, we do our step 3, which is divide by small. So I'm going to divide all of these numbers by 0.00388. When I do this, I end up with 3.02 carbons, that's close enough to round to 3 carbons, 5.93 hydrogens, that looks close enough to round to 6, and then 1 oxygen. So now I have an empirical formula, C3H6O. I could also go one more step and find a molecular formula. So remember, my empirical formula from before was C3H6O. And you want to ask yourself, well, what would the molar mass of this substance be? So what I do is I add up the mass of 3 carbons, 6 hydrogens, and 1 oxygen. And that would give me a molar mass of 58 grams per mole. And it looks like my molar mass of the actual substance is somewhere in the 100 range. So it looks like this is about double. So if this is my empirical formula, my molecular formula would be twice that. So I'm going to double everything and make it C6H12O2.